In this video, let's read about and explore on the Search Autocomplete System. Now, this similar components and this learnings can be applied to autocomplete, search as you type, design top, K-most search query system, etc. So, in it can be mentioned in any way. Still, all the components, the concepts, and what we are going to learn stays the same. So, you must have seen the Search Autocomplete System. Let's say you visit google.com. Over in the search complete tab, you mention coffee and you can see a lot more options popping up below that. So let's say coffee near me, coffee nearby, coffee maker, etc. So how do we populate these options is what we want to achieve. There could be maybe 500, 1000, 2000 options, but we need to populate the most queried and the most popular ones. So let's see the requirement gathering. Top K frequent, which is the topmost K frequent ones which we need to populate out of the all the queries which we have with us, which all users have searched. So this we will limit it to mostly 5 most popular queries. Then we need to sort them on the basis of their frequency. That the topmost 5 popular ones we need to show up here to the user. Let's ignore case sensitivity to keep things simple, and we will treat all characters as lowercase. We need to scale our system to somewhat support 10 million daily active users, and we need to make our system highly available. To give users a better experience, we need to respond back with results within few hundred milliseconds, somewhat like 100, 200, 300 milliseconds or so. As the user is typing actively, they want as minimal latency as possible. So this makes sense as well that the users are typing their queries in the search box, and we need to populate these top 5 most frequent queries searched by the users overall. These populated queries need to be responded back to the user and populated on the UI in as low time and as low latency as possible for the users to have the best user experience. We don't want the users to wait for a couple of seconds or so for the queries to get loaded up. Let's see back of envelope estimations for our systems for the requirement, which is 10 million daily active user, which we need to achieve. So we took 10 million daily active users. On average, say each user does 10 queries per day. Okay. So 10 times 10 million daily queries, as we had 10 million daily active user, each user doing 10 queries. So that becomes 100 million queries per day, or QPD. Say now one query, which I showed you above, let's say coffee. Similarly, we can have other queries. So on an average, say one query has 7 to 10 characters in it. So on each character being typed, one call is being made, right? We need to make one call because on typing each and every word, the context of the overall word or the sentence can change, right? So 100 million, which we saw, which were the queries per day. Then on each character, we are planning to make one call. So 7 to 10 characters, so 7 to 10 queries multiplied by that. That makes it 700 to 1000 million queries per day, which is somewhat 11k QPS or queries per second. So we need to scale our system and make our system highly available so that it can support as high as 11,000 queries per second. Now let's see for storage. Say one character takes 1 byte of memory, right? So 1k or 1000 million bytes per day we had, right? Which equals to 1 GB per day, and 2000 GB for 5 years if we take up 5 years of storage, or 2 TB for 5 years considering peak load traffic and all unique queries, plus all unique queries, which is on the worst case scenario. So we can see 2 TB is nothing. So storage seems fine. We want to make our system highly available is what we want to handle 11K QPS, even though we can have eventual consistency. So we need to make our system highly available, even though we can have eventual consistency. We don't want very strong consistency. That is fine. If another character gets popular at a very recent time, let's say in maybe some time, right? So we are fine if eventually that gets populated upwards, right? And also for the real-time use cases, we will see at the end how we can handle that use case for some queries getting too much attention and too much popularity in very less time. But for now, we are okay with that. As I just mentioned, this is what I have explained here. So no harm in showing X popular keyword over Y, where Y recently got highly popular, and eventually showing Y in our top K or top 5 most frequent searched keywords, right? So as we can see, and if you want to read more about that, why we can't have very strong consistency in parallel to having very high availability. So you can go and read a little bit more about CAP theorem, where we can achieve any two of AP or CP system, because we need to have network partition tolerance. So we can only achieve very high availability or very strong consistency. So seeing our use case, we are good with picking up the AP system, which is having very high availability and also having network partition tolerance, which is a must. Now, this can be divided into two flows, as we saw. So from a very high level, we can have one flow as having a data gathering service to gather the searched keywords data and store them somewhere. Okay. So user is typing some keywords. We need to gather all this data, do some computations on that, and then store them somewhere. Then second flow is to have query service to extract top K popular queries from the gathered data as the user types in. Now the users on the other hand are typing some keywords or queries, and we need to fetch results from the gathered data and figure out the top K or top 5 most popular or most frequently searched words and populate them on the UI to the user in as less time as possible. Let's see the DB schema for our use case. So from a very high level, we can see we need query and we need frequency, right? So query is it stores whatever user queries, and frequency is the frequency of what the user is querying, the overall frequency of that how much this query has been searched overall. For example, let's say we have query as Twitter, Twitch, Twilight, Twin Peak, Twilio, and these are its frequencies: 35, 29, 25, 21, 18 respectively. Let's say in this search bar user typed TW, and for example a top K frequent queries which we are populating is K is 2. Okay, for example, although our requirements is to populate 5, but just for an example we are taking it top 2. So what we need to populate based on the frequency as the user type TW, right? We need to fetch for the top 2 highest frequency queries, which is 35 and 29, which is Twitter and Twitch. And this is what we will populate over there, as them being the top 2 most frequent search words with prefix as TW. But using RDBMS here, say SQL, won't scale that well. Else it would have been quite an easy thing to do. As with large number of prefix, as that would be a full table scan, right? As we saw here, we took couple of TW prefix words, but the words that have prefix as TW could be huge with their frequencies, right? So there would be the full table scan for that, and then sorting them on basis of frequency, and to eventually just to limit it to 5, which is our requirement of top 5 or top K. This seems like too much time taking process. We can see that we are dealing with string operations, right? Makes sense. and extract results based on prefixes, right? So for this, we have a data structure called as tries, and this seems the best possible and optimized data structure for the use case of having string operations, dealing with that and extracting results based on prefixes. That is why it is also called as a prefix tree. So this is, I have mentioned an example over here. So for the words deal, deer, heat, hen, so and so, what will, how it would be represented as try. So let's see, for below example, what would be the try being formed. Let's say we have couple of queries which the user typed. Let's say tree, try, true, toy, wish, and win. And couple of users did these queries. So we have frequency in front of them as well, which is number of times they have been queried. So the try looks like is, you can check out couple of articles on that to read a lot more in depth about tries, but it has an empty root node. And then as we are just dealing with the lowercase characters for now, so each node can have 26 child nodes, which is basically 26 child character nodes. So for tree, it starts with T, so we will have the T node filled up. Then it will point to the R child node. Then we will get E, so TRE, and then TREE. So a tree is formed, and there it can store a value of its frequency. Similarly, TTR, and then we get Y, so try over here, and then its frequency. Similarly, from TR, we can get TRU, and then the U can point to E, its E child node. So we get TRUE with its frequency being stored. Similarly for toy, then from the root node, we can populate for W child node out of those 26 character child nodes. Then we get I, then I, from I, it will again have 26 child nodes. So I'm ignoring the other character empty nodes for each of the node to bring out simplicity in the diagram. Then we'll get wish, and then we can fill up the its frequency, which is 25. And similarly for win, which is 50. Now say user types in TR, and we want to get, just for an example, top two most frequent words. We will first reach till TR node, right? So we first reach from T, we reach TR node, we extract out all words and their frequencies. So from TR, we will visit all of its 26 character child nodes, and then to their child nodes and so on, till we are able to gather all the words, which we will be able to do that as tree with frequency 10, try with frequency 29, true with frequency 35, and toy with frequency 14. And this is what I've mentioned over here. Then we need to sort them out based on their frequency and then extract out top two words, which is 2 for our case. So we will get true with 35 frequency and then try with 29. And then these results are returned and need to be shown to the user on the UI. Now this seems like a very good approach, but if you observe carefully, this still seems like a slow system, as collecting all words of a node, right, which we did from TR, then again we are sorting them out. It all takes time as our try becomes bigger and bigger. Over here, our try seems a lot more smaller, but as it grows bigger and bigger, right? So as it grows bigger from here, right, then from here, so it can have a lot more words, and we have to figure out and extract out by visiting all child nodes and then getting out all the words and then sorting them out based on their frequency. So what will be the time complexity? So if you observe carefully, you will first have to reach that TR node. So prefix node you have to find, and that itself can be a time taking process if it's quite deep. As over here, you got it early on, but it can also be found quite at a deeper level. Then time complexity of extracting all words of a node which is traversing each of its child nodes. Makes sense, right? And then sorting them out and then extracting top k words from that based on their frequency. So prefix node find. Now this will perform poorly as we have to go deep in a try, as I just mentioned. But users generally don't type in too much in an autocomplete box. That also is quite true. So we can limit it out to say less than equal to 50 characters or so. So to avoid going too much into depth of a try, we will limit the users of typing till 50 characters or so. So we don't have to go too much into depth of the try for the prefix node find. Then extracting all words from a node in real time. This can be optimized if we cache the final k words and their frequency at each node. So when the user is querying these words, right, what we saw is this, we were doing it in real time. Like once we visited the TR node, we were collecting all these words by visiting all of its child nodes in real time, right? So this we can optimize if at every node we store the result, which is the top k most frequent words. And we know that that won't be getting updated too quickly, right? So this is what I've mentioned. So we cache the final k words and their frequency at each node, so that once we reach a prefix node, we can get top k frequent words from the cached nodes in it and big O one time directly, rather than going to its in real time its children nodes and collecting all the words from it and then sorting them out again in real time. So we can store all of this at every single node. So once we reach the prefix node, we are good with it. But this comes with a trade-off on storage, as each node we have to store few other nodes with their frequencies, basically the results, so we have to cache them, which will be fine as we saw in back of envelope estimations, as we were very much okay with the storage. Now we can use Redis redisearch module, which handles this use case and gives pattern or phrase exact matching, fuzzy searching, etc. So you can read a lot more in depth about the redisearch module and the features that it gives out of the box. Everything gets handled internally by Redis. Let's see with a couple of examples how things will be done. So this data is stored, for example, let's say Elon Musk interview with a frequency of 1000, which is 1000 times it has been queried. Then Elon Musk net worth, it has been queried 800 times. And then electric cars, it has been queried 500 times. Now say a user comes and it searches in the search box as EL and asks to get, and let's say just for simplicity, we have a top 2 most frequent search system, which will get the top 2 most frequent or the highly popular queries till now, which has a prefix of EL. So out of these 3, it will get us Elon Musk interview, which had a frequency of 1000, and then Elon Musk net worth, which had a frequency of 800. And all of this will be internally handled by the Redis redisearch module. One thing we can see in real world system, that once a try is built for popular keywords or the search queries, it won't change that often. So we can have the try constructed at some interval rather than constructing it once and updating plus managing it throughout. So updating and managing a try is a lot more complex and painful rather than constructing try after certain intervals. And you can see with a lot of these autocomplete search systems, the search queries and the keywords which are quite popular don't change every now and then. So for our 2 flows, which were data gathering service and user query service, let's see how to approach the high level design and certain components involved as part of that. So let's start with data gathering service first. Based on what we discussed above, we can take user inputs and quickly append them to append only log file or AOL. So user inputs, user queries will keep on coming and we will simply keep appending them to a simple append only file and returning back that we are good. This file can have all the user queries or keywords and their timestamps. Then we can have an aggregator service. It can run at a frequency of say maybe per day, per week, etc., depending upon what our use case is, which we can discuss with the interviewer. Then this aggregated service collects all the data which is appended and present of the search queries and their timestamps. So let's say it is based on per week. So this aggregated data will get or extract all the data in the log file based on the timestamp of last 1 week. And then it will store user queries, their respective frequencies and timestamps in the aggregated DB. So this aggregator service will get that data from the log file and then aggregate them based on their frequencies and timestamp, and then push it all to the aggregated DB. And these are the three things which are quite important in respect to the aggregated DB, which is the user queries, their frequencies, and then the timestamps. Then we can have our workers, which will pull data from the aggregated database, and then they will do two things. On a weekly basis, they will update the Trie DB, and then they will also update the Trie cache, which will have a weekly snapshot of DB. When user queries, we will get the results from Trie cache first to get faster response, as it will have the weekly snapshot of our Trie DB. So workers responsibility is to pull the aggregated data from DB, construct the tries, and push it to Trie DB and also store it in Trie cache. For persistent storage, we can use, so for our Trie DB, we can use S3, MongoDB, etc. S3 can be used as it provides versioning, immutable snapshots, etc. But you can definitely check out MongoDB and go with that option as well. Now the data can be serialized into JSON or stored as flat binary or compressed, etc. on the S3 blob storage. To save memory on cache, we store Trie data up to only a fixed prefix length and say top 5 most frequent words for each of the prefix, as we discussed above. Now, rather than storing even the whole weekly data of all the user queries, their timestamps, their frequencies, as we are doing with the Trie DB, we can limit and save some memory on Trie cache by storing only the prefixes up to some certain fixed length and storing just the results of that, which is the top 5 most frequent words for each of the prefixes. Now let's see what we need to do from a very high level for the query service. So let's say user queries something, it goes via load balancer and hits our API servers. Now API servers, what they will do is pull data from the Trie cache and load it and respond back to the user, so it can be loaded on the UI as quickly as possible. And Trie cache, as we saw above, has the weekly snapshot of the Trie DB. Prefix gets matched in Trie cache, then we return the top k most frequent words from the cache itself. As we saw, that will be big O 1 time complexity. Trie cache holds the most recent weekly snapshot from Trie DB, as I just mentioned. On top of all of this, to further speed up things and for the users if they are querying repeated things, so we can enable browser caching as well. So for similar typed queries, user gets back the response even more quickly. On this, we can have TTL of few minutes, hours, days, etc. depending upon our use case. Then we can also have a filter layer in front of our Trie cache, so that harmful, explicit, etc. queries can be filtered out at an early level itself, and this filter layer can be further configured to block certain type of content. This can guardrail our system from populating harmful, explicit, or that sort of content. Our current system is good, but unable to handle queries that get too much popular too soon, say within couple of minutes or hours, right? That makes sense. Currently, our Trie cache and Trie DB has weekly snapshot of data, which aggregator service pulled from the log file, append only file, aggregated, did some computations and pushed it to try cache and try DB. But let's say Elon Musk did something, and it can be that everyone is searching about it, right? So this comes under the case of getting too much popularity too soon. For example, under a couple of minutes or hours. Now we can't just rely on, say, our weekly snapshot try data. So all the users querying, say, EL will miss about Elon Musk recent thing which he did, right? Because that has been become popular recently only within a couple of minutes or hours. And our data coming from try cache or try DB has the weekly snapshot of it, which it might not have that things done by Elon Musk or OpenAI or something more recent. So we need something in this short time window as well. On a high level, user is searching something. So we will bring data definitely from try cache, which has the weekly snapshot, but we also need this live data. So what we can do is bring data from try cache, have this live data, and then merge results from two of these things. And this merging can be done on the basis of, let's say, impressions, weight based upon recency, and couple of other factors. That how much impressions it got, how much weight that query is carrying based upon its recency, based upon its impressions or frequency or its popularity, and couple of other factors, right? So to handle this live data thing, Kafka streams can be helpful. We can add this layer where every search event gets published to a Kafka topic. So on a high level, let's say we have a Kafka topic search events, and then our event payload looks like that we have the query, which the user type, let's say Elon Musk, and then its respective timestamp. Kafka Streams logic will break it into prefixes. We can configure all of that. So let's say we user typed Elon Musk. So Kafka Streams logic will break it into prefixes. So let's say EEL, ELO, ELON, then ELON space M, and so on. Again, over here as well, we can limit prefix to few characters, say 15 to 20. Then the next thing would be to aggregate searches on these prefixes over a certain window, say few minutes, 10 to 15 minutes or so. This is done at some local state store. So for example, we have this prefix EL. So this will now have 50K searches in, let's say, last 10 minutes. And this searches and its frequency on this prefix and this window, which we have, right? So window, frequency, prefix, all of this can be aggregated at some local state store. Then all of this data, we can push this data to Redis under, say, trending with some TTL added to it. So when user searches for EL, we get data from Redis from both worlds and merge them based on, again, couple of factors what we discussed above.